KAUST and the leader of Sense Lab. So I think Marco is bringing us today how to accelerate deep learning via controlled, compress, and manage communications.
Okay, so thanks again for this kind invitation. It's great to be here at this KAUST workshop. So I'm going to tell you a little bit about the work that we've been doing over the past few years on accelerating deep learning, which I think it's not one of the KAUST projects, but maybe it could be, maybe some opportunities for integration. So let me get started by saying, how much I actually enjoy living in present times, because we really live in a virtuous cycle where great data scientists, great students, and whatnot can create increasingly larger models thanks to increasingly larger data sets, and this is just happening as we continue. But one thing that is happening under the surface is that all this great innovation is being enabled by costly infrastructure that keeps on also growing and evolving. We train a lot of these models nowadays thanks to hundreds of machines equipped with many accelerators, GPUs, DPUs, and whatnot. And yet, the compute requirements for some of these workloads are doubling at impressive rates. OpenAI had recently told us that they see the compute requirements for some of the largest models doubling every 3 months. And so I'll be probably not so surprising in saying, training these kind of models can still be very time consuming, whether that is in days or weeks, energy consuming, and ultimately cost. So of course, to make machine learning more efficient, we want to scale. We want to help scale. There's a lot of interest in that. It's probably $1 billion, not more problem worth tackling. And so as we grow with scale, we want to, in spirit, we want to make very efficient use of multiple resources so that we can train using massively parallel amounts of resources, of GPUs, over multiple worker nodes, large models. But this unfortunately incurs significant overheads that are due to network communication that happens. So here is some measurements that we've done in our work, where as a percentage of the total iteration time, we show how much of the time is being spent over network communication in 2 different settings at the 100 gigabit or 10 gigabit per second for various models. And on the left-hand side, we're showing models that tend to be larger and also more recent, where you can clearly see that even going from 10 to 100 gigabit network may not really be sufficient to remove these operates. So the work that we've been doing is essentially trying to answer this question. While AI workloads remain primarily compute intensive, since they are not really scaling well due to communication costs, can the network be the next kind of accelerator for scaling machine learning? And I'll be focusing on the most common form of parallelizing DNN training, which is the data parallel settings, in which you essentially parallelize the model. You create a replica of the model at a worker, you split the data samples, and you go compute over mini batches locally at steps, making steps of SGD or some other optimizer. But at the end of the day, you have partial gradients computed that you need to synchronize. And that synchronization entails form of all-to-all, very intensive communication pattern where data that is in the same volume as with the model, so hundreds of megabytes, if not gigabytes, need to be synchronized. So if we take a closer look at what happens during synchronizations of this gradient data, we determined that distributed machine learning really scales poorly due to this communication cost. And from the infrastructure perspective, we have all this data just traversing the network, and the network is really oblivious to that. Whether you're using standard solutions such as reduced collective communication or distributed parameter servers, the network is still really not helping you. So we're asking, is there something that the network, the infrastructure really could help with regard to this problem? And we leverage essentially some recent trends in the networking industry that led to the development of programmable data planes. So what I'm showing here is a hardware box in which there is a programmable switch chip known as Tofino, initially was the company called Barefoot, now it's Intel Tofino, that can process 6.5 terabits of packets of network traffic per second using multiple ports. At that time, it was 100 gigabit line rate processing. Now we have scaled up to 400 gigabit, for example. So based on that technological trend, we created the system we call SwitchML, in which we co-design machine learning, distributed machine learning, with the network it supports that it needs to be very efficient at scale. Now, programming this kind of devices can entail several challenges. First and foremost, because you can only really map a limited amount of computation, and you don't really have storage on the devices. You can have hundreds of kilobytes of data, so you cannot store gradient data or model parameters as if you were to implement a very fast parameter server. Also, there is no floating points, which is the backbone for SGD. And since this is a networking problem, inevitably you have to deal with packet loss. So our design, therefore, is a co-design. So we really try to combine advantages that come from the switch machine architecture together with the leveraging host-based capabilities for any kind of processes that could not really be offloaded efficiently into the data plane. And we design a streaming aggregation protocol that is pool-based. I'll show you in a second what that entails. We also work with quantized integer operations to define the lack of floating point support, although we have done some more follow-up work trying to also support floating points directly. And we designed our own failure recovery protocol around a custom-made implementation of RDMA, because at the end of the day, what you want is to aggregate the data and send it to the GPUs as quickly as possible. This is a project that was also done in collaboration with Microsoft designers and engineers at Intel and at the University of Washington. So I'll tell you about the streaming aggregation protocol we designed with this kind of like simplified illustration. Suppose that your machine learning job has two workers, and what you see here in shades of reds and blues are your partial gradients that you need to aggregate. So we view the switch as a pool of aggregator slots where we stream data using some kind of deterministic way of splitting up the gradient data and mapping them into those slots in such a way that every worker is streaming, is coupling in the streaming. And whenever the switch notices that one particular aggregation slot is full, it broadcasts back to the workers a copy of those aggregated gradients. And implicitly, that serves as a signal that now the worker, there exists an empty slot inside the switch, and the worker can send the corresponding chunk for that slot that has been aggregated. And this operation, keeps on going with this tight coupling of the communication until we have exhausted all of the data that we need to aggregate. And the advantage of this kind of architecture as compared to doing something like overreduce, which is peer-to-peer based, or even a parameter server, is that we really afford the workers to use the entire line rate, the entire bandwidth on the network, and we have very low latency for doing the synchronization.
So just some clarification.
Yes.
So the actual addition of gradients happens on the switch itself.
The actual aggregation, which is an addition, yes, is an integer addition, and it happens on the switch itself.
Got it. That's why you mentioned the limitation about
Yes.
floating point.
Yes.
So I'd be interested to hear how you overcame that limitation.
Yes, that's a very valid observation. So in order to overcome that limitation, because we can only do fixed point integer aggregation, we perform integer-based quantization by adopting a per gradient chunk scaling factor that is computed by finding the maximum across all the different related blocks or chunks of gradients ahead of time. So, at step n-1, I can determine essentially for a block. This is the max value that I would have for the gradients in block n. I can compute that across the network using the switch, and I can determine a scaling factor. And on the basis of that scaling factor, I essentially try to maximize the dynamic representation for converting from floating points, say 32-bit floating points into 32-bit integers. So this turns out that can work well with machine learning because there is enough stochastic robustness to it that small errors will not really affect convergence. And in addition to that, many values of the gradients really tend to be small. So with a sufficiently large scaling factor, 32-bit integers are sufficient. In practice, empirically, we observe that indeed this works quite well. This is a ResNet example. We have several more examples in the paper, in which we show that by training with SwitchML, one can converge in a similar number of steps to a test accuracy that comparable to the original unquantized network.
And if I might just ask another question in the middle of the talk. So you said it was, I heard the words 32-bit integer quantization.
Yes.
So you're going from a 32-bit floating point to a 32-bit integer. So, obviously from an information theoretic perspective, there's an opportunity to lose nothing there because it's still 32-bit information. But I'm curious what is actually lost in that conversion from a 32-bit FP to a 32-bit integer.
In a lot of cases, the error really could be very, very small. And the reason is that a chunk here is basically a packet worth of information. So it's essentially 1024 gradient values that we aggregate at a time. So you're really trying to scale from a floating points to, say 1000 gradient values. You may be in the situation where your scaling factor is a value, which is a floating point value that is sufficient that you could represent all of the dynamic range of those particular 1000 gradient values. In the worst case, you may have an error, right? So that could be akin a little bit to gradient compression. I will touch upon that, but there can be an error in representations, no doubt. Now, since we're doing this for speed, I'd just like to convince you that this is actually worth doing. And so here I'm illustrating a speed up as compared to the NVIDIA NICO or-reduced library at 100 gigabit per second, where we can see that for various models there can be a speed up of SwitchML up to 2.27x for particularly very large model deep line, which is a couple of gigabytes and has a lot of exposed communication. That is, there's a lot of communication that is not overlapped with computation. And of course, this kind of ratio, the speed up changes depending on the computation ratio. Now, these were experiments executed on a fast network, but with relatively old GPUs, the ones in orange, which were P100s. So as a thought experiment, we thought, what if we had a 10x faster GPU, which would correspond easily to an A100 and H100 these days. And so we saw that essentially the speed up would also increase for other models such as VGG and in general for all the other models that you see on the left. There is a faster speed up. The second nice property of this design of SwitchML as compared to something like Ringo reduced is essentially that the scalability is much better because performance ends up not depending on the number of workers. And so in this plot, I'm showing the throughput in terms of aggregations, millions of elements, of gradient elements aggregated, where you can see that the SwitchML throughput is very, very close to the maximum RDMA output that would essentially be the bandwidth of your RDMA transfer, as opposed to NICO, which suffers theoretically a 2x factor plus some overheads. But then also in terms of scalability, as you increase the number of workers going from 4 to 8 to 16, it also lowers its performance because its latency component depends on the number of workers. So it looks out. So switching gears a little bit, but still, on this train of thought, we started investigating a little bit deeper about this gradient data that we are now aggregating over the network. And we noticed that for a lot of the models that have large embedding layers, like the CTR prediction models, the language model, they tend to have a lot of sparsity, meaning that a lot of the individual coordinates of the gradients could be 0 or very, very close to 0 values. So we asked the question, how can we efficiently aggregate these sparse gradients? It would not make sense to really optimize with SwitchML while sending a lot of zeros over network. So we extended the protocol of SwitchML into another system we call OmniReduce that does sparse streaming aggregation. That is the input we assume to have sufficiently high sparsity. And then we split the data into different blocks as we did for SwitchML. But we had some metadata that essentially tells us from the point of view of each worker, this will be the next block index that contains non-zero data. And the idea is that we want to skip over all the zero blocks. So in order to do that, our aggregator essentially has a little bit richer logic than SwitchML switch, and it maintains a global next block. So it maintains enough metadata that it can tell to every worker, this is the time that you actually need to send your block, and this is otherwise the time at which you only are on the receiving side. And this is a single thread of computation. We parallelize this over many different threads to saturate essentially the network bandwidth. The advantage of this is that we are further able to accelerate SwitchML. So this is a speed up plot where the baseline is SwitchML itself, and OmniReduce could speed up SwitchML up to 2.23x faster on a 100 gigabit network. I should have it that this was a software-based implementation of SwitchML, the protocol that I showed before, for fair comparison, since we started building OmniReduce in software, we were not really sure about the capabilities of the switch, but in the end, we also made it work on the switch itself. So the blue bars is the speed up of OmniReduce. The orange bars instead is what you would get if you were to just take PyTorch and use their default ORGather-based sparse ORReduce methods today, which is definitely not comparable. We also had quite some success with OmniReduce in that there's a Chinese company, Meituan, that adopted it for some of their workloads. Okay, so now I'm going to really switch gears. I'm going to tell you about some other work in which we actually take a completely orthogonal approach that says, well, if you want to speed up distributed deep learning, instead of just aggregating data really fast, you could reduce the volume of data that you send over the network. There's two main families of techniques, either quantization, where you reduce the bit width in terms of presentation, or sparsification, where you try to sample and send only just a few elements. And this actually raises an interesting trade-off, because it's no longer really just the efficiency of transmission, but you're trading off accuracy versus training throughput, and also, in a sense, the compression and decompression efficiency, which is an element that largely has been ignored by the literature. So in order to really understand how practical gradient compression could be, we created a framework, we call it GRACE, in which we created the implementation of 16 different compressor methods, and we surveyed them, and we ran it on several different benchmarks. The finding may not really be surprising. We found that essentially there is no one-size-fits-all solution that just tell you this compression method is best overall. And the other one is that the compression indeed has its own overheads, and we need to be aware of overheads in order to really gain in terms of throughput speed up when using compression. So based on that insight, we worked on a method that builds upon threshold-based classification, which has an O(n) complexity theoretically, so it's very low overhead. But the issue is, who's going to tell you the threshold? Estimating the threshold is actually very hard, and this paper that we had in MRCs last year uses sparsity-inducing distribution and multi-stage estimation to try to quickly come up with a decent threshold enough so that your threshold-based classification can work and very fast. And we also consider the settings in which bandwidth could actually be an element that changes, so that we can couple together adaptive compression on the basis of availability bandwidth. So I'm almost running out of time, but I really have only a few slides left. So I'll tell you that we also have a little bit more theoretical work on this in terms of how to rethink the specification from a total error minimization point of view. And we've also done work with Sam, who's here in the room, on a compression method called natural compression. That is kind of helpful to work directly with the IEEE floating point formats. In the interest of time, I'll take questions on this later. So I'd just like to conclude on, since this is a workshop, something that is still brewing. So in reality, when you consider a lot of the literature with gradient compression, it's as though every worker node is actually one single GPU. But in the real data centers, you already have multi-GPU workers. And their architecture is something like this. You have a high-speed interconnect, something like MBZUAI or similar. And then you may even have a lot of NICs in order to have deliver a lot of bandwidth to the node. But everybody is kind of like thinking, if I'm going to do compression, I'm going to do either compression first locally across all the GPUs, and then, I'm going to do the reduction across all the GPUs and the compression, and I'm going to send everything over the network. Or there could be other solutions, such as compressing first and doing local reductions, and then making another kind of compression before sending over the network. So this is the topic that we're working on these days. We're even thinking, if I'm going to do something like that, and I end up with gradients that are compressed, then, why would I want to send that data over a slow PCI Express bus? Why can't I just put the NIC directly on the interconnect, maybe some kind of FPGA that can directly, where I can directly offload the cost of compression? Why should I do that? Okay, so let me conclude. So in summary, distributed deep learning is increasingly a communication-bound workload, thanks to very great advances in terms of computational accelerators. And so our work seeks to accelerate training with efficient network streaming aggregation, compressed communication that is very mindful of achieving so with low overhead, and manage adaptation to network dynamics when the bandwidth varies. We achieve significant speedups over the existing solutions. Essentially, our systems are presented today are all open source, and you can find them at the link at my website. Of course, all this work will not be possible just alone. So let me acknowledge a great network of collaborators, work within KAUST, MSR, GitHub, and Intel, as well as sponsors that we received sponsorship from Huawei and Intel as well. So with that, I can get to the questions. You can also do it.
I think, yes, it would be great to do the questions that you bring. I actually have some questions for you about the actual hardware involved here. But in the interest of keeping the schedule moving on time, Hector, would you like to introduce our next speaker?